And then we get a sign of that. So sign is that when the input is a negative one, so we transform it to -1. If the input is a positive, then we return positive one. So that's it. In this way, we can make sure that the gradients, the elements in the gradients, so they have specific range. They can be either -1 or +1. And then we multiply by a small number, that is epsilon. So epsilon is used for sample period. And then we get our perturbation. So delta is the adversarial perturbations, and we will apply the inputs. So how to apply that? We can just use the addition. Because in the memory, the perturbations have the same shape as the input. You can simply just ask them to guess the attack. And finally, in the third line, this is to make sure that the pixel ranges is in the valid range. Because when we reference images, each pixel is in the range 0 to 1. So therefore, we just click the attacks, so that the attacks are still valid images. So basically, when you implement fast gradient side methods, you can just use 3 lines of code to finish, to calculate the attacks. So let's see the results. So here, given the input and so it's an x, and then we calculate the sign of gradients. So sign of gradients, so they can be either +1 or -1 for each element, and we have RGB, because this is color image, so we have RGB channels, and then we have a very noisy perturbation. But however, we cannot apply this to the input, because this will destroy the visual information per input. So that's why we multiply it by small value. So this is the epsilon here. And finally, we get our attack. So this is the x prime. And the attack looks very similar compared to the original image. However, you can fool the original image. So when you give the attack to the model can say, well, this is a given. And more intuitively, the model say, oh, I'm 99% confident that this is a given. And this is the fast gradient sign method. So any questions about this one? So let's see more results of this attack. We can apply this attack to different data sets. This attack is just a universal algorithm, so we can apply it to different models and different data sets. And this one is a very classical one, MLSP. So this is about handwritten digits recognition. And this is the CSIT, so we'll use CSIT intensively in the subject. So we can see that for the handwritten digits, so we set the epsilon to 0.2 or 0.25, and we can get an error rate of almost 100%. So it means that we just run 3 lines of code for each image, so we can fool the model for almost 100% of the time. And the average confidence of the fooling is almost 80%. So the model is about 80% confident about the incorrect label. And we can do the same. So for CSIT, we set the epsilon to 0.1. And in this setting, we can fool the model with almost 90% of the time. So still a very high fooling rate. And also the model will be fooled, and the average confidence is more than 95%. This shows the power of FGSM. Although this is a very simple algorithm, so you can see that this algorithm is very effective to fool the deep learning models. So FGSM can be used for n-target and tactical attacks. But when we use it for tactical attacks, so this algorithm may fail to produce tactical attacks. So we call that for tactical attacks, we define our desired label. So instead of just let the model to output the incorrect result, we let the model to output our predefined result. So here is a illustration. So why the targeted attack may fail for the FGSM. So here, let's just imagine that this is the decision space of a model. So the model is doing image classifications between birds, cats, and dogs, and this is the decision space. And then given an image of a dog, so here we can see the X here. And then if we calculate the sign of gradient, so we get the direction, modify the image. But unfortunately, here we find that direction points in this way. But this time, our target label is cat. So what do we want is that we want the model to predict X right. So we want the model to predict the attack as a cat, given an image of a dog. But however, unfortunately, at this setting, when we calculate the sign of gradients, the direction points to a direction that will never enter the decision space of the cat. So although you can use the epsilon to control the size of the step, so you can let X to move slightly in this direction or with a large step in this direction. But whatever you do, you cannot let X prime to enter the decision space of cat. So this shows a case that if you are using FGSM for targeted attacks, then it may fail. Then the next question is that how can we improve the FGSM such that we can guarantee the success for targeted attacks? And here comes another algorithm that is called projected gradient descent. And this is a very classic algorithm and is also widely used even nowadays. And this algorithm is much stronger white box attack than FGSM. So here it is still a white box attack. That means that as an attacker, we know everything about the victim. And this attack achieves high performance for targeted attacks. So we can use this attack to let the model to output our predefined labels. And the key idea is that for FGSM, we just do one step. So it's very natural that we can just extend the algorithm, that we can do multiple steps. And this is the idea of FGSM. So very straightforward extension for FGSM. So now, so given the image of a dog, then we just run FGSM multiple times. But for each time, we just run a small step. And then at the beginning, we also get a direction. So with this direction, we can never enter the decision space of the cat. But however, we do it again, and we do it again. And we keep using small steps, and then eventually we can enter the decision space of the cat and then get our attack next one. So this is the idea of FGSM. And here is the pseudocode to implement the FGSM. So we can initialize the attack as the clean image at the beginning. Then when we do that, we just apply the targeted FGSM. So here, Y is the target label, and we use the minus sign here. So this is a targeted attack. And after we obtain, so after we run the FGSM for one time, and then we make sure that the attack is still within the required range. So we calculate the difference between the attack and the original image. And we try to constrain the perturbations within our predefined epsilon. Because we don't want the attack to contain too much noise. So we want to constrain the noise using LPO. And the epsilon is the constant that we define. So in this way, we can constrain the perturbations within a small range. So here. And finally, we add the perturbation, the newly calculated perturbation to the original image, and make sure that this is still a valid image. because this is an imperative attack, so we don't end up here. We will continue the loop, so we can go back to step 2 if X5 is not treating it as the target. So in this way, we can gradually change the clear image, and then we can let it end up in the decision space of our target label. So this is how PGD can improve the efficiency of FGSM. So let's see the results of PGD. So here we show the results for untargeted attacks. So the PGD can do both targeted and untargeted. So here let's compare for the untargeted attacks. And the data set is CSIT. So we set the epsilon to a very small value, 0.03. And here for the simple and white, there are just 2 models. So for the simple is ResNet. So if you are not familiar with the architecture, the customer method, the architecture will be provided in the code base. And for white is white ResNet. So white ResNet just contains more parameters compared to the basic ResNet. And here for the natural trend models, so for the simple, for the ResNet, you get over 92, for white ResNet, you get like 95 accuracy. So the first one is the accuracy of the clean model, clean images. And then we apply FGSM. Now we can see that we can decrease the accuracy to 27 and to 32. But however, if we are applying PGD, we can see that we can decrease the accuracy to less than 1% and to less than 4%. And even the same constraint for the predictions. So this means that using PGD, we can achieve much better attacks compared to FGSM. And this is very straightforward because using PGD, we just run FGSM for microtimes. So it is very natural that we can achieve better results with PGD. Any questions about PGD? And your assignment, so maybe you can use PGD to generate the attacks. So this is very, normally for PGD, is a very good starting point to try. And also the algorithm of PGD is also provided in the code base. So you can open the code base and in the attack folder, you find the implementation of PGD. You can directly copy the code, or you can call the function from the pattern file. Next is another classical attack. This is called CW attack. And for CW attack, so the name comes from the authors, because this attack was invented by Carnegie and Wagner. They are still very active security researchers nowadays. So this attack is named using their names of this CW attack. And this is another strong and also widely used white box attack. So far, what we have discussed are all white box attacks. And here for the CW attack, we focus on the L2 node version. So in this setting, we will constrain the perturbations using the L2 node. So previously, when we generate the PGD attack, so if we go back, so here actually we have the choice that we can choose the LP node. So the P can be L1 node, L2 node, so we have the choice for PGD attack. And for CW attack, so basically, CW attack has different versions for different LP node. And here we only focus on the L2 node version. So the L2 node version finds the some samples that have low distortion in terms of the L2 node. For the other versions like L0 or L infinity versions, their implementation are different. In this subject, we only use the L2 node. And the key idea for the CW attack is that we can let the target logic value to be larger than the second largest by a specific time. So what does it mean? So giving a image, for example, we are doing classification between dog, cat, and bird, and then giving the image to the model will output values for each class. For example, the first value is 1, and for the cat, the model outputs 2, and for the bird, the model outputs 4. And these outputs are called logits. So this is a term, output. So used to describe the output values and the model. And normally, after we get the logits, so we will select the largest logits as the prediction of the model. So in this example, we can see that 4 is the largest logit. Then we say the prediction is first within the image. So therefore, the idea of CW tag is that, so given an image of a bird, then the model predicts bird. However, we want the model to predict cat. So therefore, we will use that. We want to increase the value of this logit. So instead of letting model to output 2, we want it, for example, to output 20. And in this way, we can model the prediction of this image will be changed to cat instead. And this is the key idea of the CW tag. And if we go back, so for the PGD and so for PGD attack and also for FGSM, so we can notice that we do not touch the logits because we directly use the cost function. So we just give the output to the loss function, and then we calculate the loss. But however, for CW attack, we don't use the loss function. So the loss function can be cross entropy or can be other loss function, but that does not matter. What we do is that we directly operate the output logit of the model. We want the target logit to be the largest value. So in this way, we can change the prediction of the model. And this is the key idea of step attack and also the difference compared to PGD and FGSM. So in this way, we do not need to call the loss function for training. So we have to show that for PGD, you can see we need to calculate the loss. So we need to calculate the gradient of the loss function. So therefore, we need to use the loss function. So this can be a cross entropy for image classification. But for CW attack, we don't use the loss function. And also, we need to, so when we let the target logit to be the largest one, and also we want to define the gap. So for now, we want the gap, for example, we want the gap to be at most 16. And then the target logit can be at most 20. Because we don't want to increase the target logits infinitely. For example, we don't want it to be at 1,000, at 10,000, that can be too large. But if we make the value too large, then this will introduce a lot of distortions. And also in lab Q, we will experiment with the gap. When we choose different gap, this will affect the distortion. So therefore, we need a specific gap to control the largest output and the second largest output. So the gap is used to control for the prediction confidence. Okay. So and given these different logits, so we can see that so for this output, so later in our first day, we will talk about softmax function. So basically, when we get the logits, so we don't return the logits to the user directly. Instead, we will change the logits to probabilities. And this is done by the function softmax. We'll talk about it when we talk about model stereotypes. So basically, for softmax, the input is the logits, and then the output is the probabilities. So for this setting, like 124, then let's give an example. I don't calculate it numerically. That's highly likely that after softmax, then the cat probability will be at 99%. For example, for birds, maybe 2 or maybe like 0.8%, and for dog, so that can be only 0.2%. And this is controlled by the gap. So now you can see that we have a big gap between the cat logit and the dog logit. However, at another setting, So, and we erase it. So for another setting, if the gap is small, for example, the logic of cat is only like 5. So we have 1, 5, 4. And then after solving max, then the probabilities for predicting cat will be much lower. For example, just example for cat maybe is 56%, we say this is a cat. And for birds, we just like 41%. And the remaining probabilities will go to 4. So when the difference is larger, then the difference in the probabilities will also be larger. So that's why we say this gap, the logic gap, is also used to show the prediction confidence. And we'll talk more about the softmax later. But here we only need to know that. So given the logic, so we need to control the gap between the largest logic and the second largest logic. And also, as we have just discussed, if the gap is larger, that means more distortions. So we will show empirical results soon. And for the setup attack, this is very straightforward to modify it for untargeted attacks. So for now, we will discuss the setup for targeted attacks. So given the raw characters, for example, like 1, 5, 4, is the image. And then the tag image correctly classified. Then to modify it to attack the attacks. Then it's very straightforward. So instead of increasing the logic to modify them, we can decrease the logic for the correctly classified data. That's very the natural extension for this double attack. So we are talking about the idea. So any question about the idea of double attack? And then we will talk about how to implement this idea. So here's how to implement the L2 version of the setup attack. So basically, we need to solve a minimization problem. So here, let's look at each notation first. So to generate the setup attack, so basically we need to solve a optimization problem. So let's look at the notation first, and then we can explain what we are solving. So here the TANH is the tangent function. So for the tangent function, you will convert a real number to the range -1 to 1. So it will convert a real number to the range -1 to 1. So it's a tangent function. And here, this is a graph for the tangent function. So just wait a moment.
After you go through basic lecture,
So this microphone works.
can do the quiz already. Yeah, you have to
So actually, in this subject, we will see a lot of complex formulas. So, and then how to understand them, we need to understand them like part by part. So when we explain each part, then we can understand the meaning of the whole formula. So here the first thing is the tangent. And this is the tangent function. It will convert a real number to the range -1 to 1. There's the graph for the tangent. So given it any real number, then the output will be between -1 to 1. So this is the graph of the tangent function. Then in this way, so you can see that for the minimization, so this formula we have a W here. And this means that we want to modify W. So W is a variable and we can modify. And when we modify W, we want to minimize the value of this formula. So this is the meaning of the location. So W is a variable, and then you can see that we have put W into the tangent. So we use this one, like 1/2 multiplied by tangent W plus 1. This can represent the some example we want to generate. So this is y. So why this is the case? So let's look at the range of this output. So for W is just any real number. And when we pass it to tangent, then the range of the output is -1 to +1. And then we multiply it by 1/2, so the range becomes like -1/2 and +1/2. So this is the range of the 1/2 multiplied by oscillator. So when we pass W to tangent, then the range becomes -1 to 1. And then we pass it by 1. So the range becomes 0 to 2. And then we multiply it by 1/2, then the range finally comes to 0 and 1. And you can see that for 0 and 1, this is a valid range for pixels, because we are generating images. So remember that when we generate, like when we use BGD or FGSM, and yet we need to clip the range into 0 and 1. And here we mathematically guarantee that the output of this formula is in the range 0 and 1. So therefore, we can simply consider this term as x. This is because the range is guaranteed to be valid range for pixels. And then, if we replace it by x prime, so it's very easy to understand the first term here. So we calculate the difference between the tag and the original image. And we calculate the L2 node. But here we use the squares, so square L2 node. So in this way, when we minimize this term, so we want to minimize the difference between the tag and the original image in terms of the squares L2 node. So that's the meaning of the first term. And let's look at the second term. So the second term, we have a function f. So what is f? So f calculates the gap between the target logic and the largest one. So also let's start with an example. So cat, dog, and bird. So given the image of a bird, then we want the model to classify it as dog. So this is our, so this is what we want to do. So just give it some example values. Cat is 1, dog is 2, bird is 4. So this is the output initially by the model. And then at the end, we want the logic corresponding to dog to be the largest one. So we want this value, for example, can be 10. And this is what we want. And this can be achieved by optimizing the function f. So let's see how we can achieve that. So in the definition of f, so we can see that we have two max functions. So for the max function, we give it two results and it will output the larger one. So that's the max function. Or we give it a set, then it will output the larger one set. So let's look at the internal max one, the internal max function first. So in the internal max function, so for the z, I, it denotes the ith logic value. And T denotes the target label, so that is dog. And then K specifies the gap, so we'll talk about the gap later. And okay. And then we can see that for the internal max, so what it returns? It returns, so given the set for all the logits, and here we can notice there's an equal sign here. So for all the logits except for the target one. So it means that for the target one is the dog. So we want all the logits without the dog logit. So we want the logit of cat and bird, and then we get the largest one. So actually that is the current prediction. So that's bird logit. So we get the bird logit. And then we calculate the difference between the bird logit and our target logit here. So therefore at the beginning we find that, oh, this is 2, because 4 minus 2 is 2. And then we want to, so if we ignore the minus here, and then we directly do the optimization, so we just want to minimize this gap. So at the beginning, when we calculate the gap between bird and dog is 2, and then what we do is that today's microphone has not worked well. Okay. So we get the gap between the current correct prediction as birds, and then we calculate the difference between birds and dog to get 2. And here we notice that we want to minimize this gap. So the 2 is too large. We want this to be a negative value. So what we can do is that, so when we optimize this, so when we minimize this, so what will happen is that the logic for birds will decrease, and the logic for dog will increase, because we want to minimize the gap. So this is what will happen. After some iterations, and then sometime later, we can see the logic for the dog can be, for example, can be 5, and the logic for bird will be smaller, can be 2. So at this time, we can see that we change the prediction from the birds to the dog. And this is a concrete example that when we minimize the internal max, if you actually raise it, and so that will be clear. So we have cat, dog, and bird. So the target label is dog, and the ground truth label is bird. So giving an image of a bird, the model correctly outputs that this is a bird, and the logic is 4. So for the dog, the logic is 2, and for the cat, so it's 1. But however, we want to attack the model. So we want the model to predict that the input image is a dog. So what we want to do is that we can get the largest logit that is not the target. So this is what us mean by the internal max. So we get the max logit that is not the target one. And on this setting at the beginning, that will be the logit for the correctly classified label. So that's good, logit of bird. So and then we calculate the difference so between the largest logit and our target logit. So the target logit at the beginning is the logit of dog, and given the initial value, so the initial value can be 2. Because this is a positive value, so it means that the model will not predict our target label, because our target label is not the largest one. So therefore, we want to minimize this. So here is the minimize. So we want to decrease this difference. And what will happen is that we will decrease the logits for the birds. At the same time, we will also increase the value for the dog. So after some iteration of the optimization, for example, we can see that the logit for dog can be 5, and the logit for the bird can be smaller, for example, 3. At this time, we change the prediction. from birth to door, because now the largest label or the largest budget is our target budget, and we succeed. So this is what happens when we optimize the internal one. However, we don't want to do it forever. If we do it forever, then we just decrease the gap forever. So for now, you can see that if we calculate the gap again, so when we at this position, so for the cat is still 1, for dog is 5, for bird, the budget is 3. And then if we calculate the internal max again, so we get the budget that is not, we get the large budget that is not the target. That's 3 minus 5, so now the gap is minus 2. So if we continue the optimization, this gap just goes smaller and smaller to minus infinity. That's not what we want. Because empirically, if we make the gap too large, then we will introduce too much distortions. So therefore, we need to control the gap. So we don't want this gap to be too small. For example, for now, maybe minus 2 is okay. So we don't want it to further decrease to minus 3 or minus 4. So we don't want that. So as long as we can fool the model, so that will be okay. And this gap is controlled by K. So how K works. So here, for example, we can see that, so just as an example, we set K equal to 2. Therefore, minus K here, that is minus 2. And what we calculate is for this max, so we have internal max and also we have external max. Then for the external max, so we calculate the larger value between the gap and a constant. So minus K is just a constant. So this means that if this gap goes below minus 2, for example, the gap is minus 3 or minus 4, then the external max will just return a constant here, because it just returns the larger value between the two values. And in this way, if we just return a constant, so that's f, so for example, f just returns a constant, then we cannot modify the value of f by modifying the value, because the constants does not depend on the value. So therefore, the optimization is stopped if the gap is larger than the set value. And this is how we can control the gap, so by setting the K here. Okay. And then we can see that for the first term, it controls the imperceptibility. We want to minimize the difference between the attack, so the X prime and the clean image. And for the second term, actually we want to control the fooling power. And also we use a constant K to control the gap. And then we have another constant C, so this is just a parameter set. So C is used to weighting between different terms. For example, if C is 1, then doing the optimization, so we optimize these two terms equally. If C is a large value, for example, C is 100, then during the optimization, we will give more weights to the fooling power. So this is the law of C. So C balances the imperceptibility and the fooling power. Okay. So this is CW tag. So maybe the most confusing one is the Q max function. So to understand that, you need to split this formula into two terms. So you look at the internal max and then the external max. So for the internal max, we just calculate the gap between the largest budget, that is not the target budget, and the difference between the largest budget and the target budget. So we minimize the difference at the same time. We control it by a gap. So this is CW tag. And then you may wonder, how can we really do the minimization? So doing optimization, we can just give the task to an optimizer. For example, in the code provided in a code base, you can see that after you formalize this term, and then you can just let the add-on optimizer to do the optimization. and you let Adam know that we want to change the value, the variable is W. So Adam will change the value of W to minimize the term that we given to it. And technically, this term can also be considered as the loss function or cost function. So you want to minimize the cost function by changing the value of W. So that's the CW tag. So in your lecture, you will see how CW tag is implemented. So you will see how we can implement this double max function. Okay. So any question about this CW tag? And later, when we talk about the intellectual property protection, we can see that the idea of CW tag, like the double max, will also be used when we protect the IP of a deep neural network. So let's see some empirical results. And also in lecture, you will run your code and repeat these results. So we can see that for K, it controls the gap. And then if we increase K, it means that we increase the gap. So we let the model to be more confident on the prediction or on the attack. So when K is 1, you can see that we can introduce some small noise. And then if we increase the gap, so for example, we set gap to 80. So in this one, like cat, dog, and bird, if the gap is 80, so for example, we can have like the logic for dog can be 100, for birds maybe 20, and for the cat maybe 10. So you can see that it's a very big gap. The model will say, 99.9% this is a dog, and maybe only 0.01 or 0.001% this is a bird or cat. So when we increase the gap, you can see that actually we introduce more distortions. So the perturbations, the sound perturbations are more visible here. So this is CW tag. So any questions about the CW tag? So let's continue. So we have talked about 3 white box attacks: FGSM, PGD, and the CW attacks. And now let's talk about gray box and the black box of some examples. And basically, in your assignment 1, task 1, you will develop gray box attacks. And for gray box attacks, so it means that we have stricter assumptions than white box attacks. So for white box attacks, we know everything about the tactic model. And for gray box attacks, we only have partial knowledge of the tactic model. So for example, we may know the architecture of the tactic model, or we may know the logic output from the tactic model. So, but we only have partial knowledge. And a classic setting that we cannot compute gradients with respect to input data. So this is a normal assumption for gray box attacks. And this is also true for your assignment 1, task 1. So your assignment 1, task 1, you cannot use the tactic model to calculate gradients because you are developing gray box attacks. So we assume that you cannot directly use the tactic model for gradient calculations. And besides gray box attacks, we also have black box attacks. So for black box attacks, this is the most practical attack in the real world because we have the strictest assumptions. And in such settings, the adversary only observes input and output pairs. So the adversary can only observe the input is a dog and then the output is a random dog. So that's it. That's for the black box attacks. So in this way, the attacker do not know the internal workings of the attacker model. And also the attacker cannot calculate gradients with respect to input data. So this is the gray box and black box. So here we can see that for white box attacks, we can calculate gradients with respect to the input. So we can apply FGSM, PGD, or ciphertext. But here, we cannot do it because we don't know the internal workings of the target model. And then how can we fool a model at these settings? So here is the strategy for black box attacks. So basically, the strategy is that we can train a similar model on similar data compared to the target model. So for example, we know that the target model is a image classification for cats, dogs, and birds. And we can also use the images of cats, dogs, and birds to train a similar model. And ideally, it will be very perfect that we can train the same model architecture on the same training data. This is not guaranteed because the target model may not release the training data. And so in practice, if we know the training data or we know the architecture of the target model, actually this changes the black box assumption to gray box assumption. Because at this time, we know something about the target. And also this is a setting for your task one, assignment one, task one. Because in assignment task one, we know the architecture of the target model. And also we know the training data for the target model. So that's why task one is a gray box attack instead of a black box attack. Okay, after we train our own models, so here we want to train our own model. So using similar architecture and similar data, and then after we get our own models, so we can generate white box attacks on this model. And this model is also called a surrogate model. So because we own this model locally, so we just train the model using our own hardware. So we actually have access to everything of the model. So therefore, so nothing stops us from generating white box attacks on this model. And after we generate these attacks, then we can pass the generated attacks to the target model and to see that whether we can fool the target model. However, if we just simply follow this strategy, it's not guaranteed that the attacks will succeed because there can be a difference between your training model and the target model. So this is a very intuitive strategy that can be used for black box attacks, and soon we'll discuss how to improve the attack success rates in this section. And the intuition behind this strategy is that similar models trained on similar data will be similar. So giving these similar images of like cats, dogs, and birds, and giving similar model architectures, and the target model can be very similar compared to your own model, even though you train your own model locally yourself. So therefore, we generate attacks using your own model with the white box success, and it's likely that you can attack the black box model. Okay, and here are the results. So let's see whether the simple strategy can succeed. Okay. So in this setting, we just train a single surrogate model. So it's a single model approach. And we then with this single surrogate model, we generate attacks using this single model. And then we pass these attacks to a target model. And here we can see whether it can succeed. So in table 1, so table 1 is for target attacks. Table 2 are for target attacks. And for each row, it means that we are training this model locally. So the first column represents the local model we train locally. And then for the other columns, they are target architecture. So for example, we are training a ResNet at 152 locally. And then after we generate the attacks, we pass the attacks to a black box ResNet 101 or a black box VGG 16 or a black box Kubernetes. And here, for the target attacks, so we can see that this method actually can achieve some success rates. So, for example, like when we train a local ResNet 152, and then we pass the Antarctica tax to, for example, BGG16, we can see that we can fool the tactical model at 20% of the times. This shows some success rates, but not very high. And also true for the other settings. For example, if we are training Google Net locally, and then we pass it to full ResNet 101, so we can achieve better results, almost 40% of the time, we can fool the tactical model. Okay, so for the Antarctica tax, it seems okay. But then let's look at the results for tactical tax. So for tactical tax, and then we can see that the results are much worse. So when we generate the local tax against the ResNet 152, and then we pass the attack to a black box like ResNet 101, you can see that only 2% of the time we can succeed in the tactical tax, or maybe 1% of the time for Google Net. And this is universally true for the other settings like BGG16, so you can see that only 2% of the time we can succeed. So it means that if you are only training a single surrogate model using this strategy, you will not succeed for the tactical tax. And also you assign one task one, so if you are using the single model strategy, so you can see that you cannot achieve any marks. So you can only get like 0 marks for the performance. Then what we can do? So we can extend the single model approach to ensemble approach. So instead of training only one model locally, so why don't we train multiple models? And this is called the ensemble approach. And then we generate attacks using an ensemble of models. So it means that when we generate XY, so for the previous actors, we just use a single model. So single model we say that M0. But however, you can modify the attack such that the attack can fool multiple models together. So M0, M1, M2, M3. So you can train multiple models locally. And then when you generate attacks, you write the attack to fool these models together. So this can be an Antarctica attack or tactical. So this is called the ensemble method, ensemble approach. And then let's see the results. So for these tables, so here we can notice there's a minus sign at the front. So it means that in the ensemble, we do not contain this model. So for example, for the first row, we have all the models except for the ResNet 152. And then after we generate the attack against the ensemble, and then we can see that it can reduce the accuracy of 152 to almost 0 accuracy. So this shows that the success rate is we successfully generate the Antarctica attacks. Oh, okay. So by the way, in this table, so I made a mistake. So for the Antarctica attacks, actually this is the accuracy of the Antarctica attacks. So it means that for single model approach actually is effective for Antarctica attacks. So we can reduce the accuracy to, for example, 20%, like 19%. So it means that for single model approach, the Antarctica attacks actually are effective. So we can significantly reduce the accuracy to low value. But still for tactical attacks, it's not effective. So we can only have like 1% success rate for tactical attacks. And then let's continue the ensemble approach. So for ensemble approach, we can see that we can even decrease the accuracy to 0%. So it means that we achieve 100% success rate for Antarctica attacks. And let's look at another row. So for this row, we have the ensemble, and the ensemble does not include the Google Net. And after we generate the attack and pass the attack to Google Net, we can see that we can reduce the accuracy to 5%. So previously, when we generate using only BGG16, so we can also decrease to 5%, but that's only for BGG16. If you are using other models, for example, ResNet 152, so we can only reduce that to 11. But here, we can reduce that to 5. And for the other models like ResNet 50, we can see that we can reduce that to 2%. So it means that we greatly increase the success for anti-targeted attacks. And also, for the targeted attacks, we can also see a big increase. So, for example, let's see the first row. So the sample contains all the other models except for the 152. And then we can see that the success rate for targeted attack is almost 40%. So very high for targeted attacks. Because for targeted attacks, you predefine the label. You want the model to output your specific labels. And for the BGE16, and then you can see that we can get 24% success rate. And also for the other settings. So compared to the single approach, for single approach, so most of the time we just get like 1%, 2% success rate. But for the sample approach, now we can see that we can get like 30 or 40 success rates for the target attacks. So this means that using the sample approach, we can greatly improve the success rate. And also this is a strategy that you want to apply in your assignment or task one. However, when you implement the task one, so you can follow the code from the code base. For code base, for example, like PTD attack, that is only designed to attack one model. Then you need to modify the attack such that you can attack the sum of models and follow this strategy. And normally, if you train multiple models, so you can see that you can get like full marks for the task one. Any questions about the black box attacks? Let's see some empirical results. So here, given the image, and the image was predicted was like buffalo, and then we use the strategy to generate black box attacks. So this is the sample attack. So we train multiple models, and then we generate the attack. The attack will have full multiple models locally, and then we pass the attack to a remote black box model. So you can see that the image will be classified, for example, as the rugby ball. And also for the zebra, after we generate the text, the model, the remote black box model, will say, oh, this is like a bee house. However, if you look at the images closely, you can see that actually we introduce a lot of noise here. So you can see a lot of noise. But this is because when you want to full micro models, so therefore it's unavoidable that you will introduce a lot of noise. This is in the image domain. But however, so in the image domain, so it's very hard to hide the noise in images. But however, if we apply the same idea in a different domain, for example, in the audio domain, so we can hide the noise in the music. So let's see an example in the audio domain. So in this attack, we do similar things. So we train, so in this attack, we want to attack like Echo. So this is a model developed by Amazon. So this is a black box model. We don't know the architecture, and we don't know the training size. But however, we know the task of the model. So we can collect a lot of similar data, and then we train our local models, and then we attack our local models. And for images, you can notice the noise. However, for audio, it's harder to notice the noise because the noise can be masked by the audio itself. So let's see the example.
Okay.
So you can see that a malicious command actually is embedded into the music. And if you listen carefully, maybe you can notice the small noise, but that most of the noise actually is masked by the music itself.
Getting the last iHeart radio station you listen to, 98 Rock.
And the idea is similar. compared to the idea that we talked about in the image domain. So here you also train your own local model, generate a text against your local model, and then likely you will also fool a target model. Although the target model is a black model, we don't know the internal workings of the target model, but we can still fool the model. And this is the power of black box attacks. So you can play with other demos. And also you can see that the idea of some examples actually across different domains. So it does not only exist in image domains, it exists in almost every domain. And then let's try to understand why this strategy can succeed, the ensemble text strategy, why it can succeed. So we try to visualize the decision boundaries for the predictions. So here's the decision boundaries. And so in this figure, so given the image, so this is the clean image that can be correctly classified. And then we calculate the gradient of the image with respect to the model. So here, the target model is VGG16, and the ensemble consists of all the models except for the VG16. So the ensemble consists of all the other models like ResNet 101 until GoogleNet. And our target model is the VGG16. And given the image that can be correctly classified by VG16, and then we calculate the gradient. So this direction is used as the x-axis. And then we just generate a random orthogonal direction, and this is used as the y-axis. So in this way, we can visualize the decision boundaries into this space. And the origin of the coordinate plane corresponds to the original image. So here, the origin here is corresponds to this clean image. So as we generate the text, we can move the image along the direction of gradients, or also we can change the image along another direction. So in this way, we can draw the decision boundaries of the image. So we can draw the boundaries, and then inside the boundaries, the image can still be classified correctly as the fish. And then we can notice some interesting things. So we can notice that for different models, actually they share similar decision boundaries. So for the target model, that's VG16, so you can see that this boundary is here like this. For the other one, like GoogleNet, actually the decision boundaries is very similar. Okay, and this can explain the success of black box attacks. So for example, you generate attacks to fool the ensemble of models. So at the beginning, you create images at this position. And then you generate the text. For example, you move it along the direction of gradient. So you want to fool the ensemble of models. So therefore, you want to move out of all the decision space. And then you may end up here. And then, because you end up here, so you can see that you also go out the decision boundary for the target model. So this is why when we fool the ensemble of models, so highly likely we also fool the target model. This is because different models actually they share similar decision boundaries. So this can explain the untargeted attacks. And let's see what happens for targeted attacks. So we can also do the similar visualization for targeted attacks. And then, so the origin is still the fish. And then the target label is window. So we can also generate the decision boundaries for the target attacks. So all the points within the decision boundaries are classified as the target label. So given the original fish, and then we can have the x-axis. So this is the target scenario direction. So this is the, so given the fish, so we can generate the targeted scenario examples, and then we calculate the difference between the attack and the original image. And this direction is used as the x-axis. And also we can use a random orthogonal direction as the y-axis, and this way we can visualize the decision boundaries again for the target attacks. And then we can also, so in this setting, the ensemble attack contains all the models except for the ResNet 101. So ResNet 101 is our target model. And we train our ensemble model using other models like BG16, ResNet 50, ResNet 121, and MoNet. And then at the beginning, so we start at this position origin. And then we want to fool all the models to output the label window. So therefore, we need to generate attack that is in the intersection of all the decision boundaries for the sum of models. And then you can see that if we can fool all the other models, then highly likely we can also fool the target model. So target model is ResNet 101, is represented by this small decision space. So highly likely that if we end up in the intersection of all the other models, then we can also enter the decision space for the target model. And this can explain the success for the target attacks. So any questions about this? So in this way, we explain the mechanisms of the ensemble attack. So why it can succeed after we visualize the decision space, so we can explain the success of the vector space. So next we talk about physical solid examples. So previously we only talk about digital attacks. So the attacks, they are generated using evidence, and then we pass the attacks to the target model in the digital format. But however, in the real world, so most of the time we cannot touch the target model. For example, the model is deployed in a self-driving class. So we cannot pass the, for example, image or video in the digital format to the target model. So instead, the model will use the camera to capture the image or to capture the video, and then the video or image will pass to the model. So in this setting, the question is that, can we generate the solid examples in the real world? So for example, we generate the solid examples of an image, and then we print the image out, and that's the image to be captured by the camera. Can this still succeed in fooling the deep learning model deployed inside the target? And the answer is yes. So we can also succeed in the physical world. Actually, such attacks can cause real harm in the real world. So imagine that for the self-driving cars, and this can be fooled by the solid examples. So when we generate physical examples, we need to consider the physical world challenges. So here are some factors that we need to consider. So the first one is that we need to consider the environmental conditions. For example, the distance and the angle of a camera in the autonomous vehicle with respect to a long side there is continuous. So here we try to generate some examples. So using the long side, so we generate some observations and put the observations on the long side to fool the model. But however, the distance and angle of the camera when it captures the long side to them in the real world. And also we need to consider other environmental factors, for example, the lighting, weather conditions, etc. And besides the environmental conditions, we need to consider the spatial constraints, because we can only put our observations on the long side itself. We cannot manipulate the background. So this is not like the digital attack. For digital attack, we just can add the observations to everywhere of the image. But however, in the real world, we cannot modify the background. We can only modify the surface of the long side. And besides that, we also need to consider the physical limitations on the accessibility. So because at the end, the attacks will be captured by the camera. So we cannot make the perturbations too small, because that can just very small perturbations may be ignored by the cameras. And finally, we need to print out the perturbations. So we need to consider the fabrication error. So make sure that after we print the attacks out, the attacks are still effective to fool the model. about how to generate the physical attacks. And here we consider tactical attacks. So for tactical attacks, it's more dangerous in the real world because we can control the predefined prediction for the model. And the key idea is that we just include all the potential transformations into the calculation of the attacks. For example, when we generate attacks, we need to explicitly consider the varying distance, the different angles, etc. So we need to formulate them into the generation of the attacks. For example, the printing errors, etc. And later, so in the second part of today's lecture, we'll talk about adversarial robustness. So we will see that similar ideas actually can be also used to improve to defeat the defense. So that can be used to improve the robustness of the perturbations. For example, let the attacks to be robust against preprocessing. But here, we let the attacks to be robust against the physical conditions. And after we successfully generate the text, then the attacker will print out the attack on paper and then cut out the perturbation. And finally, just put it on the target object. Okay, so let's see, how can we modify the optimization objective? So here is a method that we can generate the attacks. So basically, we are still doing a minimization. We are still solving a minimization problem. And here, delta is the perturbations that we want to generate. Okay, so let's see the notation first. So here for the MX, so this is the perturbation mask. So what is perturbation mask? So this mask actually defines the place that we can modify on the load sign. For example, giving the load sign, so giving a picture of load sign. So basically, only load sign only occupy a portion of the picture. So for physical attacks, we can only attack the surface of the load sign. We cannot modify the background of the load sign. Because at the end, when we print out the attack, we need to put the attack on the surface of the load sign. So therefore, how can we define the surface or define the area that we can modify? And this is defined by the mask MX. So for MX, it's just a binary mask. So the size of the mask is the same as the input image. And then we have ones on the places that we can modify. For example, we have one on the surface of the load sign, and then we have zeros on the background of the load sign. So in this way, when we do animal-wise multiplication, here this dot means animal-wise multiplication. So we do the multiplication between the mask and the adversarial perturbation. And then we can see that we actually extract the perturbations that will be applied on the surface of the attack. So we only extract perturbations that will be associated on the surface of the load sign. So this is the first term. So here are the details. So for the mask, it contains zeros in the regions where no perturbations is added, and ones in the regions that the perturbations is added during the optimization. So we use mask to fit out the perturbations that cannot be put on the load sign. And also, we try to minimize the LP mode, because we still want the perturbation to be as small as possible. So like that, it will cause the suspicion from the others. Okay, so this is the first term. So M and there. So any questions about the mask? Okay. So when we apply the mask, actually we are solving this constraint, spatial constraint. Because when we modify the load sign, we can only modify the surface of the load sign. We cannot modify the background of the load sign. So therefore, we use a mask to constrain that the perturbation that we generate can only be varied on the surface of the load sign. Okay. And then let's look at the second one. So NPS. So NPS is interoperability is full. So when we minimize the NPS, so it will help us to reduce the difference between the digital representation and the final print results. So for the details of the NPS, we don't cover them in this subject. And then is the last one. So what is the last one? Let's look at the notations. So for the last one, we have XP, and this models the distribution of images containing the target object. So here we focus on the traffic side. So under both physical and synthetic transformations. So here it means that for XV, actually it just represents the different transformed target object. For example, the object can be captured, for example, the low side, so we can take images of the low side with changing distance, angles, etc. And also, we can use some synthetic ways to modify the low side. So we can crop the object within the image, or we can digitally change the brightness of the low side. And this is represented by XP. So XP, simply speaking, XP just represents differently transformed low side. Okay. And I will reduce that, we just sample a transformed low side from the XP. So XP just represents potentially transformed low side. So we have different choices to transform the low side. And then we just sample by specific transformation. And this is represented by XI. So XI is a specific transformed low side. Okay, so this is this one. And then let's look at the other term. So for TI, so here, so it denotes the alignment function that maps the transformations on the object to transformations on the perturbation. So for example, if the object is rotated, then the perturbation is rotated as well. So here, remember that when we do multiplication, element multiplication between the mask and the perturbation delta, actually we extract the delta that will be applied to the low side. But however, this XV represents transformed low sides, and XI represents a specific instance of this transformed low sides. So therefore, we need to align the perturbation between, well, we need to align the perturbation with the low side. So after we apply the mask here, so we extract so we apply the mask to the perturbation, and then we need to do the alignment. So for example, given the low side, and this low side is rotated, for example, rotated by some degrees, like this one. And then we also need to rotate the perturbations, okay? Because the perturbations will be eventually put onto the low side. So that is what is done by TI. So for TI, it will also rotate the perturbations using the same transformation that is applied to the low side. And then we add the transformed perturbation onto the low side. Okay. And finally, we calculate the loss function. So that's J. So we pass the perturbed. And we see that after we add the perturbation to the low side, then we give the perturbed low side to the model. So F delta represents the model. And in the same way, we calculate the loss function and also with respect to the calculator. So actually, for the loss function, you should be familiar with that. So that's a classical way to fool a model. So we calculate the loss function giving the calculator. J is the loss function, F is the target model, and Y star is the calculator. And then you want to minimize the loss with respect to the target label. So in this way, we can fool the model to output our target label. So this is the optimization objective that we want to achieve. Any questions about this problem? So you can split them into different parts. So for example, like this one, mx multiplied by here. So this is just a mask perturbation because we only want the perturbation on the remaining surface. You cannot put perturbation in the background. So we need a mask that can let us locate the surface of the node map. And then, so this is the first optimization. And also when we do optimization, when we use addition between different nodes. So basically when we do optimization, it means that we want to minimize different nodes simultaneously. So it means that we want to minimize the LP node of the mask, or the LP node of the perturbation. And also we want to minimize the non-interpretability score. And also we want to minimize the loss when we pass the target label. And also here, after we get the mask perturbation, because for the traffic side is affected by some transformation. For example, it can be rotated or the brightness can be changed. So therefore, we need to align this transformation. So the mask perturbation need to go through the same transformation as the traffic side before we apply it to the traffic side. So we also use the add, so the addition to add the perturbation to the traffic side. And then we just do the normal procedure where we generate target attacks. So we just minimize the loss function by using the target label. And then we just calculate. So we just solve the minimization problem to generate the physical attacks. So let's look at the results before we have a break. So here we see the physical adversarial attacks. So here the target label is the speed limit 55. And what we do is that after we generate the attacks, so we just print out the attacks and then just put the attacks on the traffic side. So here you can see that we have the store sign, and this can fool the model with 100% of the times. And also we can put different sign, so we can use different traffic sign to generate the attacks. And also the success rate is very high, more than 70% of the time. And because we are using a mask, so go back to the previous slide here. So this mask controls the area that we can apply the perturbations. So therefore we can actually have some very interesting shape of the perturbations. For example, we can specify that the perturbations, they will have some specific shape. So instead of that the perturbations to be applied on all the surface of the traffic side, we can specify some specific areas that we put the perturbations. For example, like these places. And we can also see that we can still achieve very high successful rates. So these attacks. And this shows the power of physical adversarial examples. Great. So any questions? Good. So let's have a short break. So let's continue at 5:10.
No way. They wouldn't have a. Wouldn't that everything will have it. I don't see. I don't
In the example,
This camera.
That one was only the simple lah.
This kind of food also require to remember it. For example, in the exam, maybe I give you a apple. This apple, for example, give you an apple, and then I think spell this apple to us.
Yes, it's steps.
Body can be
Yeah, for this one, maybe I just change the sign here. Even some minus sign, I change it to positive.
oh, was it targeted and not targeted?
Yeah, so you know that we are generating PD for target. That's the last test. So that's the kind of question.
No, only the not text one.
Not the super complex one.
No, not that one.
Not complex.
Maybe today can win money one, but the Brazil score the final goal the last minute. I predict the score is wrong, but the wrong time. No, I only win one time, I only win the second score first. $2.80 $1. Then the other $1, so I bet $2, $1. I bet what is Japan 2, then Japan qualify, then Japan score first, so I win the Japan score. So I lost 20 cents. Then in $10, Japanese they playing they bring very defensive, like they keep the ball far, I used to get receive by Brazil. Then 3 minutes in like the coach bring out the death note already. But they wear white no blue, they wear the jersey all white colour. Then the shit lah. Then the today the morning I was right, freaking the two match right, all match until penalty. Wow, looks very intense. Yeah. Actually, adversary means attack. The word. Do you? The word not adversary. Adversary is basically challenge. The word is chin one, right? Or the English chin.
Yesterday I asked you after the perturbation then the adversary example comes in.
Actually, the physical one, right, is the attacker will like paste like some small sticker on the stop sign, or they shine some
Confuse the area.
yeah, or shine some infrared like color, like you can see from your eye, then the sensor will to trick the sensor lah.
That's
Yeah,
especially the devil.
the lighting they change the lighting. Actually, I also low key don't get the graph, right? You know the negative fish.
The geography.
What the fish that
Geography graph.
Yes.
X basically moves towards Y is any other direction. So
This to detect why they engage, is it?
no, basically it's saying that like as you move X the gradient direction, so if you want to move like you want to move towards the here. Oh no, because the origin is the original image. So if you are within the position, that means that like is classified as like example if your image is a dog, so inside this maybe like this thing inside the position boundary of dog. But so because you technically already your model already reached that the minimum movement the local everywhere global. But like when you reach the minimum, so you move from the minimum point, like either plus or minus. Like you are you are basically moving away from, like either way you're still
Bigger
moving,
dot.
yeah, from bigger dots. Yeah, so but you also can move, but sometimes like because you can move in a direction that also doesn't move you away from it. But you can, like, that's why the one is just anywhere that like doesn't move you away. So like you can still be a dog. Like but you I mean because the decision model is not just one. It's like it's not like a specific point to say, oh, this point is blocked, it's here and it's area. Yeah, it's an area. Right. And that's why you do the when you train a model, you train this.
So it's a cluster basically. Yeah. It's clustering. So this circle is like your dog. But once you go out of this circle, already you're pet something.
Something like that, but I won't use the term clustering because clustering is something else. Yeah. Yeah, but yeah, the idea is and this one is just like so between your origin. So if you want to move it, there's something like goldfish. You make a dog goldfish, you want to move it inside. Then you have to move to what like the gradient. You have to move your, like example, the image, your original image, right? In the decision space, the goldfish, area is somewhere different. So you have to move in the direction you want.
You need to know the model reading. I thought it's very complicated. That means the attacker.
No, but his point is saying that like because okay, I mean how I think about it is like a goldfish will always look like a goldfish. The goldfish will not look like an arm. So because of that, a lot of models it is referring to the same object. Many models might have similar boundaries. Right? How they decide whether it's a goldfish? Right? Okay, maybe it's golden color. Right? It's maybe it's shaped like fish, for example. So because goldfish, like a lot like even different models, so like they would have similar or at least they are similar architecture. Yeah. So in this point like all this is like the boundary of the different they become overlap. So if you want an example, I mean in this case is the one that is small. So is it that if you train towards like if you combine the different models, right, you know the model like your like the model that you want to attack, you don't know what architecture they do, but this one is different models. They might have the same boundary, or they most likely have the same boundary. So if you combine different models, you train towards the direction, there's a high chance when you attack that one, you will also see the direction. Yeah. It is the reasoning for why it says from there.
Because in the end, you know, the model somehow is
Like
the boundaries, the decision boundaries is something.
In the break, you can also consider if we do not apply the mask in this, what's the difference? By default, we have the mask here. If we do not have the mask here, can it work or we must have the mask here? Just look at it first.
No, that's the target data. Because your J is your cost function. Basically, you're trying to minimize. You're training towards. What you're training towards is so you're trying to get it to output that. Yeah. So you want the observation. So this is the target, like you want the observation to generate again this output rate. Yeah, but I don't really just first one. And then this is the model. This is the only test. Location, how do you locate where observation is? Yeah, then you see the size of the
So this is meter. It controls the size.
Yeah, the size of observation. This is location.
So if this one is removed, then there needs the image, the image relativity, right?
Which one?
Right. Because so if you remove this one, this one may be too big for the image, right? So you distort the image too. Yes.
Then you're talking about removing the button.
Yeah.
The booking is referring to the population, but this mask is supposed to be within the image. Where is it? Which place? You like it's the population. So that thing, because I mean, if you think about it, this thing like this can sleep. It can be anywhere, right? So I will assume this is
And they have all those things that
you will not be fixed there.
you know what I mean? Then you will get lucky can the second one is if you get 100% perfect, you get gene. Yeah, but that's not the world. The world side, if you get 100% perfect for world prediction, you get all the opportunities. Yeah. Tutorial atas juga.
It's crazy we can have all this without
So let's continue. So first let's discuss this one. So when you implement the physical Rosario tags, somehow you forget to multiply the mask in the first term. So what will happen? Then the idea? It will make your attacks fail or does not matter. Theoretically, it does not matter. So when you implement a formula, so sometimes by accident you forget to multiply the mask here, and after the optimization, you find that you can still successfully generate the attacks. And the reason is that if we forget the MX here, so what we do is that we just minimize. So what we do is that we just minimize the ALP norm of the perturbation only. So given the perturbation, so and we just minimize the perturbation, just like we are doing with the PGD attack and that. And then if we multiply it with the mask, then what we do is that we only focus on the weighted perturbations. So we only minimize the LP norm with respect to the perturbations that can be applied to the mask or to the traffic side. And at the end, actually, is the same. Because at the end, after we generate the attacks, we will print out the attack and just cut off the invalid part. So therefore, in this formula, so we only optimize or we only minimize the LP norm with respect to the valid range. And for the perturbations in the other places, actually we don't care about them during the optimization. So they can be very big values or small values, we don't care. But at the end, we will cut them out. But however, if we forget to multiply the MX, then during the optimization, we also optimize the other invalid places. So we optimize the perturbations that will be applied on the traffic side, so this place is already. At the same time, we do not multiply the mask, so we also optimize so we also make the perturbations at the other areas to be as small as possible. But at the end, we still cut out this part. So at the end, it does not really matter if we forget multiply like this. But for theoretical rigorous, so we need to multiply it when we do the optimization, because this is the valid area that we want to optimize, at least for the formula. Good. So any questions about this formula before we proceed? Okay, and later when we proceed in the subject, you can see that we will explore many complex formulas like this. So the way to understand them is that we can split them into different parts, and then we understand them individually, and then we can understand the whole formula. And the key is that when we do minimization, when we add different terms, so it means that actually we are minimizing these terms simultaneously. So we can analyze each term just one by one, and then we can get the whole formula. Okay, and now let's talk about a new kind of adversarial attacks. And this is called universal adversarial perturbation. Actually, this is task 2 in your assignment. So far we have generated perturbations for specific inputs. So given an X, we generate delta. Delta that is specific for this X. And the question is that, can we have perturbations that can be applied to any input? So we don't want the delta to be specific just to one X. We want to generate a delta, and the delta can be applied to any X, so that the result can full norm. And such perturbations are called universal adversarial perturbations, and UAPs for short. And here first of all, we talk about an targeted attack. So whether we can generate universal perturbations for an targeted attack. So we generate a universal, so it means image agnostic perturbations. And the perturbations should be small, because we want the perturbations to be acceptable as much as we can. And when we apply the perturbations to an image, and then the image will be misclassified by the model with high probability. And it means that we successfully generate the UMPs. And here, the goal, we can formulate the goal using these two lines. So we want to find the perturbations that satisfy the following two constraints. So here we slightly change the notations here. So because these notations come from the original work. And also this is a kind of bad news in deep learning literature. Because in deep learning, it's not like math. In math literature, everyone uses the same notations strictly. But for AI, the literature, so some different authors, they may use different notations. But it's a small issue. So when you read the articles or read the papers, so make sure that you understand the definition of different notations. So here, we slightly change the notation. So instead of using delta, we're using V to represent the perturbation we want to generate. So at the beginning, we also want the LP norm to be less than a constant. So we specify a constant by ourselves. And then, so let's see the notations. So delta is the desired accuracy of the samples. And here for the delta, for example, we want the, so after we apply the perturbation to the inputs, we want the accuracy of the model, for example, to be only 10%. And then delta is set to 10%. Okay. And then V is the UAPs that we want to generate. And the K hat represents the time classified. So let's look at the second constraint. So for the second constraint, so X is the input image. So we just extract a arbitrary image from a distribution. So you represent the distribution of the domain image. So what we want is that we apply the perturbation to the image such that we change the prediction. So it means that when we apply the perturbation to the image and pass it to the model, then the model will make a different prediction. And we have set the desired accuracy, for example, like 10%, and now 1 minus 10% is 90%. So we have the success rate of 90%. And this is the second. The second just means that we want to fool the model by a specific percentage or specific probability. For example, 90% of the time, we want the model to predict incorrect labels when we add the perturbation to the input. And under these settings, let's see how can we generate UAPs for Antarctica health. So here's the algorithm that we can use. So we have a set of data points, so a set of images, the target model, and also the desired LP norm for the perturbation. So this is a constant. We try to constrain the perturbation. And also the desired accuracy on the samples here. And the return of the algorithm is the UAPs that are generated. So at the beginning, we set UAPs to 0, and then we start the while loop. So while loop will continue until the error is smaller than the predefined value. For example, the error is still smaller than 90%. Then we continue to modify the UAPs. Okay. So let's see what we do. So for each data point, so we just extract each image from the image set. We add the UAP to the image, and we see that if the UAP does not fool the image, and then we need to compute the minimal perturbation that sends the perturbed image to the tissue boundary. So it means that we want to calculate another or an extra perturbation, so that's represented by R, and such that we apply R as an extra perturbation to the already perturbed image. And this will cause the misclassification of the model. And also we want the perturbation to be a small perturbation. So therefore we want to do the minimization. And then the result is the small extra perturbation. So we denote it using the delta V. And then we update the UAPs. So we update the UAP, we add the extra perturbation to the already generated UAP, and we project it back using the constraint, because we need to make sure that the UAP is still within the constraint that we specified in terms of the LP model. So in this way, we keep updating the UAPs until when we apply the UAP to the images, we can fool the model with a high error rate. So this is the error. And how do you solve this minimization problem? So you can, for example, if you are using the strategy of CW attack, so you can use add-on to do the optimization. Or you can just use the PGD or etc. Because in this way, you are just fool the model. So you are actually calculating an actual perturbation and want to fool the model. So you can use CW attack or PGD to implement this optimization scheme. And the goal is that you get the actual perturbation that can be used to update your universal perturbations. So this is the algorithm for generating UAPs. So, any questions about it? So let's see the empirical results. So here we generate UAPs against different deep learning architectures. So here we consider CafeNet, BGG. Actually, in subject you will use BGG a lot for assignments and labs. And also ResNet, you will also use it. And we can see, and here we constrain the perturbations in terms of L infinity, and give it a constant that is small value. And we can notice that for different architecture, the structure of UAP actually are quite different. So this is an interesting observation. And then let's see what happens if we add the UAPs to the clean image. So here, the target model is the Google net. So given the image, for example, this image, and then we add the UAP, then the model will say this is an elephant. And also the image, so for example, the dog will also be misclassified as elephant, like this. So when we apply the UAP to an image, it will fool the model. But however, you can also notice that the UAPs can be quantitative imperceptible, especially for the background where we have the clean colors here. So this is because generation of UAP actually is much harder than generation of perturbations that can fool only one image. So for example, in the lab, when you are applying PDD or CW attack to just generate perturbations for a specific image, you can find that the perturbation can be very small. Because this is much easier to just generate perturbations for a single image. And it will be much harder to generate perturbations that can be applied to any image. So therefore, you can see that actually the perturbations are more noisy compared to the perturbations for single images. So this is the Antarctic attacks. And for UAPs, it can also be used for tactical attacks. And actually for task 2, assignment 1, you will develop UAPs for tactical attacks. And here we show an example to do the tactical attacks in the domain of audio. So here the tactical model is a speech to text model. So this model will transcribe speech into text format. So giving it a piece of speech, it will transcribe into text. So our goal is to generate UAPs. And here we are generating UAPs for tactical attacks. So therefore we need to change our perspective. Because here for tactical attacks, so imagine that we generate a UAP, so UAP is data, and then we can apply it to any audio. So the audio X0, X1, X2, etc. And then the result. So and then we can have the X0 prime, X1 prime, X2. And for all the attacks, all of them can be transcribed to a specific transcript because we are doing tactical attacks. So it means that for text-to-speech, we define our target transcripts. For example, the target transcript can be like open the garage door, so this is the target transcript. And then all the attacks, they will be transcribed into the target transcript. So in this setting, we can see that actually the UAPs is strongly associated with the target transcript. And then whenever we add any audio to the UAP, the result can still be transcribed into the target transcript. So therefore, in this way, so traditionally, we generate some examples giving an input. For example, an input of a panda, and then we generate some voice. So the panda itself is the signal, because the panda can be recognized as panda, and then we generate perturbation to fool the model. So, and the perturbation is tailored to each input. So this is the traditional idea for silent perturbations. However, for targeted silent perturbations, so as we just shown here, so we can see a strong correlation or a strong relationship between the UAPs and the target transcript. So here we can consider the UAP itself as the signal. So in the set, so we can change our perspective that UAP actually can be transcribed as the target transcript. So if we give UAP to the model will say, oh, this is open the garage. And then UAP is robust as the modification by the other audio. So given the UAP, and then even if we add, for example, another clean audio like good morning to the UAP, the result can still be transcribed as open the garage. So if we change our view, so when we generate the target attacks, then we need to change our view to understand the UAPs, especially for target attacks. So under this view, so the input is actually, we consider the input as noise applied to the UAPs. And the UAPs itself is the signal that can lead to the classification results. And also when we add the audio to the UAPs, so all the results can be still transcribed as the target label. So it means that the UAPs is robust as modification by adding different inputs. So this is a different point of view when we generate targeted UAPs. So let's see the algorithm to generate target attacks. So how can we generate UAPs to fool a speech-to-text model? And the key idea is that we can make UAPs to be robust against different audio. So because when we change the perspective, the UAPs actually are considered a signal. And then, so in this setting, we want the UAPs to be robust against some modification. And this idea actually is similar to the visual text. So when we generate visual text, we want the perturbations to be robust against physical transformations, like the changing of distance, changing of angles, etc. And here, we let the perturbations to be robust against different inputs, so different audio. But the idea behind it is the same. Okay, so let's see the algorithm. So given the tactical model, we denote it as F, a set of audio D, so that they are clean audio. And then the target phrase T, so T can be open the garage door, and the minimum success rate, so eta. So for example, we want the success to be 90% of the time. We can have the target success rate. Okay. At the beginning, we initialize the UAPs as 0 values. And also we initialize a subset. So because for text-to-speech, so to training text-to-speech, the loss function is much more complex compared to image classification. For image classification, we optimize the cross-sectional tables. So basically, so using the mathematical term, so that's only just a single line, so you can describe the cross-sectional tables. But however, for speech-to-text, the loss function is very complex. So and also the optimize optimization is much more difficult compared to image classification. So that's why instead of considering all the audio together at the beginning, we gradually consider more and more audios. So that's why we initialize a subset G. So subset G can start with just one audio, and then when the UAP is lost just one audio, we add another audio. So we increase the size of the subset. So until we consider all the audios in the set B. But however, your task 2, you are pulling a image classifier. So your task 2, when you implement UAPs, so you don't need to have the subset and then gradually increase the size of subset. You can directly use all the images when you generate your UAPs. Okay. And after initialization, then we start the while loop. So we do the while loop until iterations is less than the max number of allowed iterations. Then we set the success number, so S to 0. So S means the number of times that we fool. So number of times that we achieve success rate in terms of the subset. Then for each audio in the subset, now what we do is that if we can fool the model to predict the predefined transcript, then we just increase S by 1. So S just calculates the number of times we succeed in the subset. And also, we modify the UAPs using gradient descent. So this is just a targeted attack. So we can also update the gradient. Oh, sorry. We can also update the perturbations using gradient descent, just like what we do for PGP snap attack. So this can increase or improve the fooling power of the perturbation. Okay. And then after we do it for all the audio in the subset, then we check whether we have full all the audio in the subset. And then if we have considered all the audios, then we just return the UAPs. And if not, we just add more audios into the subset from it. And at the end, our UAPs actually can fool all the audios from the audio we consider here. Okay, so this is the algorithm. So the algorithm actually is straightforward. So at the beginning, we just let the UAPs to be, so add the UAPs that can be applied to a subset. And then we gradually add more and more audios into the subset until the UAP can be applied to every audio in the audio set we consider here. And the result, the criteria, the successful criteria is that we want the model to predict our predefined transcript. So let's see the empirical results. So for this figure, so the x-axis is the number of audios in the subset. And then, so we have just discussed in the algorithm, we increase the size of the subset gradually. So each time we add one audio. So the audio set only contains one audio at the start of the generation process. And when the UAPs can attack all the audio in the current subset, then we add one new audio to the set. At the end, we consider 150 audios. And here, the figure here actually shows the iteration trend to generate UAPs that are capable to attack all the audio in the subset. So here, the y-axis represents the number of iterations that we update the UAPs. And here, we can see that the horizontal axis actually represents the number of audios used to train the UAPs. And the vertical axis shows the number of iterations that for the UAP to attack all the audio in the set. So previously, you can see that in each iteration, actually, we still update the UAPs. And here we have some interesting observations. And then at the beginning, so when the size of the set was small, then the number of iterations actually increased as more audio was added to the set. So here at the beginning, when we generate UAPs to fool only one audio, so we just look at the minimum or we just look at the mean iterations. So maybe we need to run at 25 updates for the UAPs. And then if we want the UAPs to run more audios, for example, like 10 audios, then maybe we need to run the iterations for over 40 updates to update the value of UAPs. So we can see an increase at the beginning. Actually, this is reasonable because it's harder and harder to make the UAPs to run more audios. So it's very straightforward. And however, we can notice a very interesting trend. So the iterations started to decrease when the size of audio sets reached around 20. So here we can see a top value here. So when we consider 20 audios, so around 20 audios in the set. And then if we consider one more audios, actually you can see a decrease in the number of iterations. So for example, if the UAPs are already able to fool like 100 audios, then if we add just one more audio, maybe we just need to update the UAP just for one time. The UAP is okay to fool the new audio. So this is like just a very interesting moment. So it's an aha moment for UAPs. So it shows that when UAPs are robust against a specific set of audios, then it will be easier and easier for the UAPs to fool other new audios. So this can be observed from this trend. So when UAPs are robust against a large set of audio, then we need few iterations to find a solution to attack newly added audios. So this is what we can observe when we generate the UAPs. Any question about this figure? Yeah, this figure actually, so you can consider it in another way. For example, when you train a model against some like randomness, for example, the Gaussian noise, and then when the model itself is already robust against the noise, and even if you increase the noise a little, the model can still be robust. And it's similar in this UAP generation. So when the UAP is already robust against 100 audios, then even if we add a new audio to the set, so the UAP highly likely is still robust against the new audio. So in some cases, maybe we just need to slightly modify the UAP for a couple of times. So UAP can be adapted to the new added audio. Yeah. So let's see more results. So let's test the generalization of the UAPs to unseen inputs. So in the previous figure, this is the figure for training the UAPs. And we use a set of data, like we use 150 audio. And then we will check that after we fix the UAP, whether the UAP can be applied to the new audio. So that audio are unseen during the generation of the UAPs. So here we apply UAP to all audio with duration between 2 and 4 seconds from the testing set. So these audios are not seen during the generation of UAPs. And here the horizontal axis represents the number of audio used to train UAPs. So here, so for example, the 100 here, it means that the UAPs can be used to fool 100 audio, and the UAPs can be fool 150 audio. And the vertical axis shows the success rates of applying the UAPs to over 700 audio with a duration between 2 to 4 seconds. And here we can observe that the success rates of UAPs increase clearly as more audio was used for training. For example, when we have the UAPs that can fool 100 audio, we have the success rates at around 90. However, if we only have the UAP that can fool like 25 audio during the generation, the success rates when we apply UAP to new audio is just like 40%. So this also shows that when UAPs are robust against a large range of audio, actually UAPs also show better velocities against the thin volumes. Any questions about this? So in your task 2, so you don't need to, so we have just discussed, you don't need to sequentially increase the size of the size of the images that you apply UAPs to. So you can just use all the images, because for image classification, the optimization is much easier compared to the text to speech or speech to text models. So also we have discussed that when we generate tactile text, we change the perspective that UAPs are single and the UAPs are robust against the other audio that can be added to the UAP. So we do experiments to see that whether UAPs are indeed single. So we just push the UAP to the model, and then we let the model to transcribe the UAP. And here actually we see that the UAP itself actually shows the properties of a real audio. So for the UAP, if the target transcript is use airplane mode, and the slice means that we use the first, for example, first 10% of the UAP, or the first half of the UAP, or the full UAP. So you can see that as we use more and more slice of the UAP, actually show this similar property compared to a real audio. For example, the first 10%, it will be transcribed as use. 50, for example, like 30%, it will be transcribed as use airplane mode. So this shows that UAPs are really single after we generate the UAPs, because UAPs actually can be transcribed by the model as the type phrase. But this is not true for the perturbations that is designed for a single input. For example, when you generate perturbations for a single image, for example, the perturbation that can fool the model to say this is a given instead of a panda. And then you give the perturbation to the model. So the model, highly likely that the model will not say the perturbation is a given. So that perturbation is mixed with the panda image to fool the model. But for targeted UAPs, the story is totally different. For targeted UAPs, the perturbations are just signals. So you can input the perturbations to the model, and the model will give you the target transcript. So this is a UAPs. Okay. And we are talking about the five examples that are constrained by the P-law. So when we generate perturbations, we constrain them by the P-law. And however, in practice, P-law is not necessarily a good metric to measure the stability of the perturbations. So because if we just have one pixel offset, then we can result in a large P-law. So given an image, for example, we have just a vertical bar at the middle, and then if we just move the vertical bar just one pixel, for example, to the right. So actually the two images look almost, or we can say the two images look the same for human eyes. But if we calculate the P-law, so you can see that the P-law can be very large. So this means that if we only consider P-law to constrain the perturbations, actually it's not a very good metric in the practice. So therefore, people invent other perturbations, and that is not constrained by the P-law. One example is spatially transformed style examples. So for these style examples, instead of just add the perturbation to the input image, so we can move the pixels. So just we can move the pixels along. For example, here we can see that we just move the pixels at this position. We just move it to the right a little. And to humanize, so this is still a handwritten zero, but in this way, it can also fool the model. And this is a new kind of style examples. And these perturbations are not constrained by the P-law. So actually, if you calculate perturbations between the inputs and the original clean image, so you can see that the pinhole can be very large. But however, to human eyes, they are very similar. And also we can use the generative models to generate the attacks. So here are the example. So the image A here is the ground for the ground truth label in the image A is the present. And the first one is the original image. And then we can use generative models to change the color. For example, like this one, we change the color to red, and we can add a model to say this is umbrella. And this way, if we calculate the pinhole can be extremely large because we change the color of the image. But as long as the attack look reasonable, so it is still a valid attack in that case. And also for the image B, if we use the generative model to change the ground color to blue, and we can fool the model to say this is a patch instead of the color. So as long as the image looks reasonable, so this is a valid attack. So that means that nowadays researchers change their opinion that pinhole may not necessarily be the only constraint that we apply to perturbations. As long as the attacks look reasonable, actually they are valid attacks. But however, for such images, you can see that the generated results are very strange. But this is because this was from an early work that is like 7 years ago. And now, as the authors know that the generative models, they have improved a lot in the recent years. And then if you use state-of-art generative models to fool the model, so you can actually generate very good attacks. So for example, the left figure is the clean image, and the right one is the attack. For example, you can use the commercialized generative models. For example, you just slightly change the light of the color of the sky, or change the color here, and then this can fool the model. And also for the strawberry, so for the clean image, the strawberry is like this one, and then you can use the generative model maybe to slightly change the strawberry, you can fool the model. And for such attacks, they look very natural, and they are valid attacks. So although when you calculate the LP rule, for example, infinity rule, it will have very big infinity rule. So however, to humanize, they are very reasonable. Oh, sorry. And this is the neutrality of the some examples, and they are called unrestricted the some examples. Okay. So we have talked about the some examples. Any questions? So after talking about the attacks, then naturally the next topic is how to defend against adversarial attacks. And let's talk about adversarial robustness. And here's the outline. So we'll talk about adversarial training. And then we'll talk about using input transformations as defense. And then we'll talk about how to detect the adversarial examples. And finally, we talk about some reflections on adversarial examples. For example, like while we are studying adversarial examples. Okay. The first technique can be used to defend against adversarial examples called adversarial training. And so here, after we notice that the attackers can generate the example to full model, then the question is, how can we train deep neural networks that are robust against adversarial inputs? And to solve this question, so we can use a optimization view of the robustness of adversarial robustness. We can use, let's say, center point problem. So what is center point? A center point is any location where all the gradients of a function vanish, but which is neither a global nor local minimum. And here is a sample illustration, sample illustration for a simple formula. So here we visualize the formula of z equals to x squared minus y squared. So here we can look at, so here we can notice the saddle point at the middle. So you can see a right point here, and this is the saddle point. And the whole image looks like a saddle, and this is the reason why this is called a saddle point. Okay. And then we can also use the same view to consider saddle robustness. So when we want to train a robust model, so actually we'll need to solve a saddle point problem. So we have a maximize inside and also we have a minimize outside. So actually the formulations of this type have a long history going back to 1945. So we can view the saddle point problem as the composition of the inner maximization, so here maximization, and the outer minimization. And for the inner maximization, so you should be familiar with that. This is the way that we generate attacks. So the delta is the perturbation, and S means the weighted range, for example, the LP rule. And then we want to maximize the loss function. So L is the loss. So when we apply, so Y is the ground truth level, so we apply the perturbation to the clean input, and then we want to maximize the loss. So this is the way we generate and target attacks. So this is the inner maximization problem. So the inner maximization problem aims to find the adversarial version of a given data point X and achieves a high loss. So this is the way we attack a deep neural network. And then for the outer minimization, so this minimization problem aims to find the model parameters that are robust against the attacks. So that's the adversarial loss given by the inner attack is minimized. So although we want to generate attacks in the inner maximization, however, at the end, we want the model to be robust against the adversarial samples. So therefore, we still need to do minimization. So we want to find the model parameters actually that can lower the loss value with respect to the attack. So that the model can still correctly classify the attacks. And that's the purpose of the outer minimization here. And the outer minimization is the problem of training. It's the problem of training a robust classifier using the adversarial training techniques. So why this is a saddle point? So we can see that regarding the loss function, so the attacker, they want to maximize the loss function. So they want to achieve the maximum point of the loss. However, for the defenders, we want to minimize the loss functions. So we want to decrease the loss functions. And at the end, we will reach at the saddle position that no one can proceed anymore. So the attacker cannot increase the loss anymore, and for the defender, we cannot decrease the loss anymore. So that's why we can consider the adversarial training as a saddle point problem. And theoretically, correctly classifying of samples requires a stronger classifier. So here we have an illustration of different classifiers. So here we compare the standard decision boundaries compared to adversarial robustness of decision boundaries. So for the left figure, so the first figure here, we have a set of points. And in this setting, we can easily separate them using a single or using just a simple one. So here we have a linear decision boundaries, and then we can achieve, for example, 100% accuracy given the data points. However, this simple decision boundary is not adversarially robust because we can generate some examples, so that can be shown in the figure in the middle. So here we generate the L infinity adversarial examples. So L infinity can be seen as a square around the clean input. So clean input is the dot here, and then when we generate adversarial examples, so actually we can end up with any position inside the square. And then you can see that for some adversarial examples, or for some results, actually can go across the decision boundaries, and then it will result in the adversarial attacks. So it means that using a simple line to separate the points, although we can achieve good accuracy, but however, it's not adversarially robust against the attacks. Theoretically, if we want to generate, or if we want to train a robust model, we need a complex decision boundary. So that is shown in the figure on the right. So in the figure on the right is, so we need to separate the different data, and also the decision boundaries need to be robust against the attacks. So you can see that we need a very complex looking decision boundaries like this in the red line. So this is some theory behind the adversarial robustness. Okay, and here's the question. So given an input, clean input, if we are generating adversarial perturbations using L infinity mode, then can be seen as an utility space. So that is the square. So inside the square, all the points, they are added adversarial perturbations in terms of L infinity mode. And the question is that, what about L1 mode? So what's the shape? So giving a clean input, so this is a node. And then if we are generating adversarial perturbations using the L1 mode, so what is the shape look like? So into this space. So remember that for L1 mode, so actually that is the sum of the absolute values. So for example, we are in the 2D space. So for a input, we only have two values, that V0 or V1. So that's, for example, observation to be represented by two values. That will require the sum of them. The sum of the absolute values to be less than a constant. For example, the constant is absolute. So in this way, this will look like a diamond. So will look like this one. So it's not a square. It will look like a diamond. So that's for the L1 mode. And how about for the L2 mode? So L2 mode is just Euclidean distance. So basically giving the clean input. Then if you are measuring the perturbation using L2 mode, so it will look like a square. So your free time you can calculate or do some theoretical analysis of it. Okay, so let's continue. So let's see how we can implement adversarial training. So adversarial training itself is a very simple and effective defense. And here we can, so basically, if we go back to the center point, so basically, when we train the model, we also need to generate the attacks. So we don't train the model on clean input. Instead, we train the model on attacks. So technically, we can use PGD to generate the attacks during the training of the model. So why we are using PGD? Because empirically, people find that using PGD to generate the attacks for adversarial training can achieve the best robustness. So this is not theoretically guaranteed, just empirically observed using PGD. And then here's the Python code for silo training. So basically, we also start a for loop, and then for the for loop, we get the data. So remember that we need to set the gradient to 0 at the beginning. And then instead of directly give the data to the model, here we generate the text. So we generate PGD text, and then we pass the text to the model. And then we calculate the loss, and then we do the optimization. So here, compared to the normal training, for normal training, we just don't have the PGD tag. So instead of giving for normal training, instead of giving the model text, we just give the model clean input. But for silo training, we give it a text. And this is associated with the saddle point formulation. So when we train the model, we train the model using a text instead of using clean input. And during implementation, so this can be easily achieved by generating a text during the iteration of training. So let's see the results. So here, simple is just the red net, white is white net, and then the results is shown on CSIT. So for standard training, so we can see the accuracy are clean images. So natural means the clean images. So you can see the accuracy is 92 or 95, and then when we apply FGSM, you can see the accuracy decrease to around 30. If we apply PGD, you can see the accuracy decrease to below 1% and below 4%. So this is for standard training. And then if we use FGSM to generate the text during the silo training. So here instead of using PGD, we use FGSM. And we can see that the model can be robust against the FGSM. So the model can still achieve high accuracy for FGSM attacks. But however, PGD can decrease the attacks or can decrease the accuracy to just 0% accuracy. So it means that the model is totally defeated by PGD. And then if we use PGD to do a silo training, and you can see the general robustness against both PGD and FGSM. So that's why people choose to use PGD for silo training. And interestingly, you can also see that when we apply the silo training, so we also decrease the accuracy on clean input. So this is a side effect of the silo training. So although we achieve robustness, but we also decrease the accuracy on clean input. So let's see more results. So let's see the performance of thoroughly trained network against different attacks. So here we have different setup. We have the white box attacks with PGD for different number of iterations and response, and we denote by the A. So denote the results by A. And then we have the black box attacks. So the attacker just independently train a copy of the network. So it's just like the black box attacks we have just discussed before. It is denoted by A prime. And the last one is the black box attacks from the version of the same network. But however, the model is only trained on natural examples. Because here we are testing the robustness of a thoroughly trained models. So for the A natural, it means that the thoroughly model is just a naturally trained model. But for A prime, the thoroughly model is a thoroughly trained model, and it's a different model that trained locally by the attacker. And here we can see the results. And the most successful attacks are in both here. So we can observe that the thorough training lowers the model accuracy on natural clean data. So for example, if we just train the model only using natural images, so we can see that the accuracy is, if we evaluate the thoroughly trained models on natural images, so we have a decrease in the accuracy. Because for clean images, if you recall that, you can see that for a standard training, we can achieve over 90% accuracy. But here we only achieve 87. And then for web post text, so we can see that PGD is still the most effective text against the thoroughly trained models. But also CW tag is also very effective, so just 1% difference there. And then for the black box attacks, so we can see that PGD is still very effective to transfer to the thoroughly trained models. So using PGD, we can decrease the accuracy to 40 or to 64%. And however, from the point of view of the attacker, if you only have a standard trained model and then you apply PGD, and then you can see that you cannot succeed. The accuracy is still 86. So it's very similar compared to accuracy on natural. So this shows that using PGD for stereo training actually achieves overall good robustness of stereo attacks. However, there's a limitation for stereo training. So we can observe that the stereo training is very slow. This is because when we train the model, we need to generate the text in each iteration. So here, remember that for PGD, we have the for loop. The for loop may run, for example, like 7 times, 10 times. And this is done for each iteration when we train the model. This can greatly increase the training time. And this is the main limitation for the stereo training. Because when we train the model, the biggest, so the slowest operation is the backpropagation. So backpropagation is where we calculate the gradients, and this consumes most of the computation when we train the model. But however, when we generate the text, remember that we need gradients. So therefore, for each iteration when we generate the text, we calculate gradients. And this way, actually, we calculate gradients for many times when we run the stereo training. And this can significantly slow the training slow. And then the next question is that, how can we improve the stereo training? So how can we improve the efficiency? And here we notice that when we train the model, so actually anyway we need to calculate the gradients at least once. Because anyway we need to update the model parameters. And this was done when we run the backpropagation with respect to the loss function. So actually we calculate gradients. And the problem is that because we calculate the gradients at least once, then can we exploit this to generate attacks? So instead of generating attacks using an individual function, can we use the gradients that are calculated here to generate the attacks? So if we can reuse the gradients, so actually we save a lot of computation for stereo training. And the answer is yes. And this comes the technique, which is called stereo training for free. So the key idea is that the gradients of the loss with respect to the inputs actually is computed on the same background path when we update the model parameters. And here's the algorithm. So using this algorithm, we can implement the stereo training without introduce the computational overhead. So here are the inputs. So we have the training samples, so they are bit X. And now we have the perturbation plot, so epsilon, and also learning weights. And then we have the hope steps, so we'll talk about hope steps later. And at the beginning, we initialize the model weights, and also initialize the delta. So delta is the stereo perturbations, initialize the to 0. And then we start the training equal. So here, for simplicity, we just set m equal to 1. So we can just ignore that for this, for now. So we just start the equal, and then in each training equal, we get the mini batch. So this is a standard training procedure. Okay, and m is 1, so we don't consider this for now. And after we get a mini batch of data, so what we do is that we need to update the model parameters. So this is the normal procedure. So we update the model parameters using the stochastic gradient descent. Therefore, what we need to do is that we need to calculate the gradient with respect to the model parameters. So this is what we do actually when we train the model. So we calculate the gradient, but however here, because we are doing observer training, so we still apply the perturbation to the input, and then we calculate the gradient. And then we run the gradient descent. So we update the theta in the opposite direction of the gradient. So this is a normal procedure we apply when we train the model. However, here the key trick is that when we calculate the gradient with respect to the parameters, so that is where we call the loss dot backwards. So that's when we call the back propagation. Actually, when we call the backwards propagation, we get all the gradients. The gradients includes the gradients with respect to the parameters, and also we get the gradients with respect to the input. So they can be obtained just in one pass. So this is implemented in PyTorch. So therefore, we can save the observer gradient. So remember that when we generate a text, we need the gradient with respect to the input. And here, actually, we get the gradient. Although, so this is got together when we calculate the gradient with respect to the parameters, but we get it just in one pass. Okay, therefore, after we update the model parameters, so we don't stop here. We just apply the PGD style data. So we'll calculate the sign of the observer gradient, and then we update. So we update the perturbation, and then we make sure that the perturbation is in the gradient range. So this is in this way, actually, we reuse the gradients when we train the model. Instead of call extra backwards propagation, we just call the backward propagation and this twice. Because this backward propagation anyway it must be equal for us when we train the model parameters. But at the same time, we get the gradients with respect to the inputs. So we don't just discard the gradient here. We keep the gradient, and then we follow the strategy, just like we generate the text using PGD. So we get the sign of the gradients, update the perturbation, and here you can see that the perturbation is also applied to the input to generate your text. Okay. So here is how we can reuse the gradients. And then to mimic the PGD style update, then we introduce the hope steps. So because for PGD, remember that we calculate the gradients for multiple steps. So we run the gradient, so we update the perturbations in a formula. So we need to, so here, we want to mimic the same strategy used by PGD. So therefore, we introduce a formula here. So for m times, so m is a parameter, that's called hope steps. And in this way, we just follow a similar strategy used by PGD. So giving a mini batch, so giving a mini batch of inputs. So we just follow a similar strategy like PGD. We generate the text using an iterative procedure. For example, here if m equals to 5, then we generate the text using 5 steps of PGD. And here, so to keep the same number of iterations in training the model. Here, that's why we need to divide the total number of inputs by m. So that's why we have a division m here. So because, for example, at the beginning, if we want to train the model for 100 inputs, and then for each mini batch, we play the mini batch. So here we follow the style of PGD, and then we set m equal to 5, then it means that for each mini batch of data, actually we visit 5 times. So therefore, we cannot run the original 100 iteration, 100 epochs anymore. So 20 epochs will be enough, considering the same number of training iterations. Okay, so here the outcome of the final training for food. Any questions about this one? So you may notice a issue here. So here we have introduced an extra M, so that is whole steps. So for example, so M is used to mimic the strategy of PGD. But however, if we give it a very large value, for example, we set M equal to the number of epochs. So what will be the problem? So the most straightforward problem is that for the epoch here, so we only run epoch once. And then for each, for example, the epoch is 100. And then for each mini batch, then we will revisit it for 100 times. And then we will never visit it again during the training. So this will give a very side effect. So it will decrease the performance of the model. So for example, when you train the model, give it the image of dogs, and then you replay the dogs to the model 100 times. And then the model will never see the dogs again. So this will decrease the performance of the model dramatically. So if we set a big value for M. So therefore, in practice, we need to choose a appropriate value for M. So here we can see the performance for different M. So the value M controls the mini batch replay. And a large value of M can hurt the performance. So if we choose a large value for M, then the model can forget the learned knowledge, because it takes a lot of iterations to see the same input. And here, we can see that if M is set to the number of iterations, for example, at 200, you can see a big decrease in the model performance. And however, if M is a small value, so the decrease is still controllable. So for example, if M is 4, so it's almost the same. So at the beginning, we have the 95, and then if M is 4, we have 93, so it's also still okay. And if we compare this adversarial, or if we compare the adversarial training for free with the standard adversarial training, so here's the standard adversarial training. In the standard adversarial training, we run PGD for 7 steps. So we can see the performance baselines here. So it's almost like that. We set the M to 16. Okay. So let's see more results. So here we compare the adversarial training for free with the standard adversarial training. So for the natural training, we can see the accuracy is this one, 95, is very good accuracy. And then, but however, if we apply the tax, we can decrease the accuracy to 0 very easily. So because standard trained models are not robust against the attacks. And then let's look at this standard adversarial trained models that with 7-step PGD. So we can see a decrease in accuracy, but however, it shows robustness against the attacks. So it can still preserve around 45% accuracy on the attacks. And then let's look at the adversarial training for free. So if we set M equal to 8, so basically we can achieve comparable accuracy on clean input compared with standard adversarial training. And also we can even achieve slightly better robustness against different attacks. And the key is that using adversarial training for free, so we can see that we barely increase the training time. So standard training is like 780 minutes, but for Scenario training for free, at most 800 minutes. So we barely increase the training time. But however, if we run standard Scenario training, those we have discussed, the standard Scenario training is very slow. So you can see a big increase in the training time. And here you can see that compared to standard training is almost 7 times. So you can see a 7 times increase. So can you see why this is by 7 times? So why it's not 10 times, 20 times? It's around 7 times. But this is because for the Scenario training here, we run PGD for 7 steps. So as we have discussed, the backward propagation is the most expensive computation when we train the model, and also when we generate the text. So here we generate the text for 7 times. So it means that we do backward propagation for extra 7 times. So that's why when we compare the naive Scenario training with the standard training, so we can see an increase about like 7 times. But this is not true for Scenario training for free. For Scenario training for free, because we use the backward propagation. Therefore, we do not increase the training time. At the same time, we can achieve comparable robustness compared to the naive Scenario training. However, so for the Scenario training, so although we can improve the efficiency, however, there is still a limitation for Scenario training. The Scenario training is not robust against novel attacks. This is because the idea of Scenario training is that you generate attacks during training of the model. So therefore, the robustness is actually specifically designed for the attacks. And in practice, the attackers can invent new attacks. So that is very different compared to the attacks when you train your model. So here's an example. We have the Scenario training using PGD. So using our different models, ABCs, so just you can know the details of the models. And then for all the Scenario training, we use PGD as the attacks. And then we apply the spatially transformed Scenario examples. So we don't include the details of this attack to this object. But the assumption is totally different. So we have just discussed this attack belongs to unrestricted Scenario examples. So it's totally different compared to PGD attacks. And then we can see that, so this table shows the attack success rates, so not the accuracy. This shows the attack success rates. So for Scenario trained models, so it's okay. For the other attacks like the GSM, CW attack, we can lower the attack success rates to below 5%. But however, if we are applying unrestricted attacks, we can still achieve almost like 50% attack success rates. So this is the limitation of Scenario training, because the Scenario training is tailored to the specific attack. So during the training procedure. So if we invent like novel attacks, so which is very different compared to the attacks used in Scenario training, then we can still defeat the Scenario trained models. So this is a limitation for this. So any questions so far? Okay, so we have talked about the Scenario training. And then, so for Scenario training, the goal is that we train a model that is robust against Scenario attacks. And then we can have another defense, so which is to use input transformations as defense. So the idea is that, so we can transform the inputs before feeding them to a model. So the transform means that given the image, that image classification, we can rotate the image, or we can flip the image, or we can, for example, change the brightness of the image. So before we feed the image to the model. And this is done both, so at both training and testing time. So in this way, we can destroy the Fusarial perturbations. So because when we generate the Fusarial perturbations, actually the perturbations have a particular structure for the type model. But however, if we transform the Fusarial examples, then the structure can be changed so that we can destroy the Fusarial effectiveness of the attack. So for this kind of defense, the goal is to remove the Fusarial perturbations from input images. And at the same time, we still need to maintain sufficient information in input image to correctly classify it. Because we don't want to just destroy the image. So in that way, even though we can defeat the Fusarial samples, we still destroy the performance of the model. So here are some transformations that we can use to destroy the Fusarial examples. So the first one is the ensemble cropping with scale. So actually, this defense is used in assignment 1, task 3. So task 3 is the optional task. So if you complete task 3, you can get some bonus task, and this bonus task you need to defeat the input transformations defense. So the first transformation is the ensemble crop scaling. So it means that given the image, we can generate some random, so we can crop the image into some random pieces, and then we just give all the crops to the model, and then we calculate the average predictions over the random image crops as the final prediction. So this is the first transformation that we can do. And we can also use the bit depth reduction. So we can perform a simple type of quantization that can remove small details from the image. So here's an example. So given the image of an apple, we can just reduce the details of the apple. And the next one is JPEG compression. So we can use JPEG to compress the image before we input the image to the model. So for example, we can control the quality of the compressed image. Yes, for example, the maximum quality is 100. You can set the quality to 75. And so when we give the compressed image to the model, so some details can be removed from the JPEG image. And here are two more transformations that we can use. And the first one is total variation minimization, but we don't cover the details of this transformation. So this transformation can remove the small perturbations in the image. So we can see some examples here. So the original image here, and then we apply the total variation minimization like this. Okay. And the next one is image quilting. So maybe we just stop here. So we'll continue tomorrow. So see you tomorrow. Let us stop here. Any questions before we finish the lecture? So see you tomorrow.